Mr. True. In this video, we're going to walk through or be introduced to quite a few theorems showing the relationships between chords, central angles, arcs, diameters inside of a circle, and then finish with 5 examples where we, find the measure of arcs and lengths of radiuses and such, and chords to help you get through your homework. Okay, well, chords and arcs in circles. A chord, like this segment of AB, is a segment whose endpoints are on the circle itself. It's basically a part of a line that is intersecting the circle in 2 different points, as opposed to a tangent line, which was in the last video we talked about, where it intersected a circle at one point and also just happened to have a slope which was perpendicular to the radius at that point of tangency. Okay, so our first theorem here and converse is going to look at the relationship between congruent circles, central angles, and arcs. So within a circle or in congruent circles, because same radius, going to be the same shape and size, congruent central angles have congruent arcs. Now we can measure arcs as far as length or in degrees. So if our central angles, maybe they're both 40 degrees, are congruent, then the measure of the arcs are going to be equal as well, both in degrees and in length. Now, I'm not sure if your book has talked about inscribed angles yet or not, but a central angle is the same as or equal to the measure of the arc, if it's in degrees, of course. So if this were a 40-degree angle, that would be a 40-degree arc. And I don't know why I feel like bringing it up, but if you have an inscribed angle where your vertex was on the circle itself, the measure of that inscribed angle would be half the measure of the arc in degrees. The converse is true as well. Within a circle or 2 congruent circles, if you have congruent arcs, then you have congruent central angles. This is all come in handy as we do our 5 examples after I get done going through these 7 theorems. Okay, what's the relationship between the central angle and the chords? Well, the same basic idea, very similar to the arcs. If you have, within a circle or congruent circles, if you have congruent central angles, then you have congruent chords. So not only would we have a situation where arc AB is congruent to arc DC because these central angles are congruent, but the chords are going to be congruent as well. Now, of course, we're talking about length because that's the only way we can measure segments. You can measure arcs in degrees or length, arc length. Congruent circles and chords and arcs. Okay, chords and arcs. Within a circle or within congruent circles, congruent chords have congruent arcs. This is kind of like tying together this first and second theorem about if you have equal arcs, then you have congruent chords and vice versa. And that all stemmed from the central angle as our first 2 theorems talked about. So if segment AB is the same length as segment CD and they're within the same circle, or they're in separate circles but each of those circles have the same radius, then the arcs are going to be congruent as well. And the converse is true. With all these theorems, the converses are true. Let's take a look at the next few that we have. Theorems, that is. That would be me bumping into the door. Hey, what about chords equal distance from the center? If we're within a circle or congruent circles, chords equal distant from the center are congruent to themselves. Let's not forget that you measure the distance between a point and a line, in this case, or segment, in a perpendicular fashion. So you must have perpendicular marks here to be guaranteed that OE is the measure of the distance between the center and this chord, and OF is the measure between the center and that chord. And I can see that I forgot a notation. If the chords are equal distant from the center. So I don't need just perpendicular marks there, I need some little hatch marks to show that those distances are equal, and if so, then AD is going to be congruent to BC. Okay, diameters and chords. Theorem, that's the rest of these 3 theorems are about diameters and chords. In a circle, if a diameter, and let's not forget, a diameter is another segment that has its endpoints on the circle, so it's kind of like a special type of chord, but the diameter is going to contain the center of that circle. So it has a special name because it's kind of a big deal. In a circle, if a diameter is perpendicular to a chord, then it bisects the chord and its arc. So if this diameter is perpendicular to this chord, then it's going to bisect that chord and break it up into two congruent parts. AE is congruent to EC, and it's going to create a couple of congruent arcs. And again, we could be talking about these arc lengths being congruent, or the measure of those arcs being congruent. In a circle, if a diameter bisects a chord which is not another diameter, see? I don't know why that exact same language isn't here, but another thing here, like look, they're saying a diameter is a type of chord. So then it is perpendicular to the chord. Kind of the same thing here. If you have a diameter perpendicular to a chord, then it becomes a perpendicular bisector. And if you have a diameter which is bisecting a chord, then it will be perpendicular. So these two are basically converses of each other, and of course they're both true. If, if segment DB that's a symbolic notation for that theorem in words. In a circle, the perpendicular bisector of a chord contains the center of the circle. So in this case, if I say that we have a chord AC, and then we have another chord, I'm not calling it a diameter, but I have another chord DB, and I notice that that chord is a perpendicular bisector of this chord, then it is going to contain the center. In a circle, the perpendicular bisector of a chord, so here's a chord and here is a perpendicular bisector of that chord AC. That other perpendicular bisector is going to be the diameter, or excuse me, not the diameter, but contain the center of our circle. And of course now if you're talking about running that perpendicular bisector and having the endpoints be on the circle itself, well then it's actually going to be the diameter as well. But this could be a line coming through, and thus that's why it's kind of not really saying that it's a diameter. This could be a line coming through as a perpendicular bisector of this chord, and we'd be guaranteed that that line contains the center. But my drawing has the endpoints on the circle, so it actually would be a diameter as well. All right, I got all those theorems done, or at least introduced. Let's see how they work in some examples. Quite a few examples for that matter. For my first two examples, this first one especially is pretty straightforward as long as we remember all of those 7 theorems I just gave you. And some of them are related to each other, so maybe it wasn't that many unique pieces of information, but quite a few pieces of information. And I've given you a couple of diameters here, or excuse me, chords. They don't go through the center. So I'm giving you a couple of chords here, and I want you to use this diagram to solve for x, or at least I'm going to want my students to solve some version of this as well. How are we going to solve this for x? Well, if you look here, you have some perpendicular marks going from the center to each of these chords, which means, and I try to draw it about as best I can, I do cheat with a compass for the circle. We got some hatch marks here which show that this segment from the center to this chord and from the center to this chord, that those distances are equal. So these chords are the same distance away from the center within the circle, which means that these overall lengths are the same. Now, I'm giving you this overall length here, down here is equal to 9, but up here this chord is equal to, or this portion of the chord is equal to x. Well, let's not forget, if I were to take this line segment and extend it right here, kind of missed there, but if I were to extend this line segment and have it act as either just a line going to the center, or if I put the endpoints on the circle, this is sort of a piece of a diameter. And I'll turn that heater off in a second. And that diameter, that perpendicular segment there is going to bisect that chord. So actually, if this portion of it is x, then this portion of this chord is going to be equal to x as well. So we have a full length of 2x is equal to 9. We divide by 2, and we get x is equal to 9 over 2. And that is that's it. That's all there is to this particular question. Now I can divide this, and 9 divided by 2 is equal to 4. 2 times 4 is equal to 8, gives me a remainder of 1 when I remove it from 9, so it's 4 1/2 units long. Or yes, as far as our value of x. And I got one more example, but I don't think you need to hear my heater running in the background of our video. Okay, here we go. We've got a circle, and we've got a diameter with a length of 16. We have a chord, which has an unknown length, which we're going to have to find. And I'll use purple first. We need to find x. Okay, well again, we have this little segment coming from the center of our circle, and it's perpendicular to this chord. And just to kind of tie in with those last few theorems I gave you that had diameter language in it, if I were to extend that and have this segment going through the center of the circle, thus being like this is a portion of and a diameter, then we know that this, you can kind of just look at the segment too. If you have a segment coming from the center and hitting a chord perpendicular to it, it's going to bisect that chord, well, bisect, cut it in half. So I'm going to solve this for y first, focusing on this little right triangle, and I'm realizing that probably looks the same as the orange chalk, so let me put white on top of this. We're going to work with this little triangle here, and we're going to be able to work with it through Pythagorean theorem because we have this leg, it's the right angle, we have a leg of 3, and this hypotenuse, it's a hypotenuse because it's going to be opposite that right angle, is equal to 8. And when you're missing only one side of a right triangle, then you can find that third missing side by doing Pythagorean theorem. So we have y squared plus 3 squared equals to 8 squared. That means we have y squared plus 9 is equal to 64. We're going to subtract both sides by 9 and get y squared is equal to 64 divided by 9 is going to be equal to, looks like 55. And I'm pausing because that kind of, was that what I had in my notes? No, it's apparently in my notes I said that 8 squared was equal to 81. I do my notes ahead of time so I can check my work. My work is now checking my notes, which I thought I checked. Okay, so I can finish this though. We have y squared, I'm just making sure. Alright, so that means that y is equal to the square root of 55, and x is equal to twice that measurement, because again, that little perpendicular segment from the center, portion of a diameter if you will, is bisecting that chord, so x is equal to twice the length of this segment. So x is equal to 2 times y, which means it's 2 times the square root of 55. And I don't know why I'm using parentheses because there's nothing else that's going to happen. Now, in my notes, I actually meant to have this be 18, which is how I got a hypotenuse of 9. And I actually like that example better because it allowed me to sort of review with you how to reduce radicals. But there is no perfect square in 55, so even though that's 5 times 11, neither 5 nor 11 is a perfect square, so this is not going to get reduced anymore. And this is the exact value version, or the exact value of our answer. If we wanted the approximated value of x, or length of that chord, we could put that into our calculator and get a decimal version and say that it's equal to, so many units, but as I just said, I made a small mistake in my notes, so I don't know what the decimal version of that is, but that is the exact value for the length of that chord. Go change my notes. You slice a sphere with a diameter of 10. Right there. Looks like a circle, but I kind of, try to make some three-dimensional-ish looking part of my drawing there, so that's supposed to help you see that it's a sphere. And you get a cross-section. Of course, if you take a sphere and you cut it, you do get a cross-section, which is a circle, so that's what this is down here. How far from the center of the sphere did you make your cut? Again, our diameter of our sphere is 10. We cut a cross-section and got a circle, basically, with a diameter of 6. How far away from the center of that sphere did we make our cut? Well, again, the diameter of this cross-section is equal to 6. And once again, for the third example in a row, we have a segment coming from the center of our sphere, and it's coming down and it's intersecting here, and it's intersecting in a perpendicular fashion. And that's how I'm measuring it. So if I do that, even though this is a sphere, kind of like this is a cross-sectional part, and we've got a portion of a chord. That chord is 6 units long, the diameter of our cross-section, which is a circle, and we're coming through and we're intersecting it because I want to measure the distance between the center and that chord, and it's perpendicular. Well, when that segment comes down from the center and is perpendicular to the chord, again, it's going to bisect it. So if this entire length is 6, then this portion of the length is equal to 3, and the diameter, while it's equal to 10, I really only need the distance between the center and the edge of the circle, or the radius, and that is going to be equal to 5. So this particular problem took longer to write and draw than it's going to take to actually solve. Sounds really complicated, but now look at what we have. We have a right triangle with 2 sides known of that right triangle, and we're only missing one side. So again, that is Pythagorean theorem. So it's going to be 3 squared plus x squared is equal to the hypotenuse of our right triangle that we're using, which is equal to 5 squared. 3 squared is equal to 9. We have x squared. 5 squared is equal to 25. We're going to subtract both sides by 9. Get x squared is equal to 16. We're going to square root both sides and get x is equal to 4. And that is how far from the center of the sphere we made our cut, which gave us a cross-section, which was a circle that had a diameter of 6. Okay, so sounds complicated, but it was just Pythagorean theorem. For our next example, we have a circle with a radius of 7 and a chord length of 10, and I want to use that information to find the measure of arc AB. Okay, well, how am I going to do that? Well, remember that your central angle is going to have the same measurement as your arc. So if I find the measure of the central angle and find out maybe it's 80 degrees or something, we'll find out what the answer is in a second, then that is going to be the same as the measure of arc AB. So really, I'm actually needing to find the measure of the central angle. So let's just say we put an O here, and we're going to find the measure of angle O. Okay, well that's fine, but depending on what you covered in your class, you might have done law of sine and cosine, or you might have just stuck with your basic right triangle trigonometry, which was SOHCAHTOA. And that's what we're going to use. We're going to drop a perpendicular down, or a radius, or not a radius, excuse me, a perpendicular down from the center, and make it perpendicular to our chord with a length of 10. That means that we will know that if this is perpendicular, we're bisecting this chord one more time, and if the entire length is 10, then this portion of it is equal to 5. Okay, so what does that mean? That means that, I could be finding, I'm not finding the length here, I could do Pythagorean theorem and find the distance between the center and this chord, but again, I'm concerned about the measure of the central angle, which will be the same as the measure of the arc. So I'm going to pull this triangle out with a length of 5 and 7, and if I find the measurement of this particular angle here, I can double it and actually know the entire measure of the central angle. Now, why can I simply double it? Because this is the radius of the circle. Over here, I've drawn another radius of the circle, which is OB, and that's equal to 7 as well. And what I'm looking at is an isosceles triangle. And I've said this now in a lot of videos, especially when we started studying regular polygons and now circles, that when you drop an altitude down in an isosceles triangle, you not only get a perpendicular bisector of the base, but you get a bisector of the vertex angle, which means you cut it in half. So if I find that angle, I can double it, and there's our answer. So I want to find, let's say, A is here, here's O, and let's add another point of C, and I want to find the measure of angle O. So I want to find this angle here. I'm just going to put a little asterisk, and that's the angle I want to find the measure of. Well, when you start working with your SOHCAHTOA, so is sine is opposite over hypotenuse, ka is your cosine of an angle is adjacent over hypotenuse, and toa is again the tangent of theta is equal to opposite over adjacent. And from this angle, we know the opposite side. I don't know the adjacent side, and to be honest, I don't want to know it. And we know the hypotenuse is equal to 7. So based off of this angle O, I have the opposite side, I have the hypotenuse, and again I'm looking for the angle. Well, opposite and hypotenuse, OH, SOHCAHTOA. We want to do sine. So we're going to do the sine of O, just remember that's not a 0, is equal to the opposite side, opposite leg of 5 over the hypotenuse of 7. That means that theta, well, I'm going into theta because all of my other textbooks I teach out of, this is geometry, but my geometry and my pre-calc and my calculus books all use Greek letters for angle measures, so let me just take that theta out there. 0, or not 0, okay, I just said it. I told you it was going to be O, and now I'm already saying 0. So angle O, the measure of angle O, let's just do that. The measure of angle O is going to be equal to, I want to get the sine function away from angle O. Well, that means I have to do the inverse math operation, or inverse sine. So the inverse sine of 5 over 7 is what we need, and that means the measure of angle O is going to be, actually, I need to correct that because I need to be saying AOC because I marked off O as the whole thing. My labeling is not very good here. So let me take this out. We'll call that measure of angle AOC. The inverse sine of 5 over 7 is equal to 45.6 degrees. And now the measure of O, but now I've complicated my diagram, so let's call that the measure of angle AOB is equal to, again, twice that, right? This was an isosceles triangle. We bisected the vertex angle with the altitude, so angle AOB, the central angle AOB, is equal to 2 times 45.6, which is, let's see here, 2 times 45 is 90, 2 times 0.6 is 1.2, so it's 91.2 degrees. And since that is the measure of our central angle, it is also going to be the measure of our arc. And I just got one more example to go. And another broken piece of chalk. Oh well. Last example. We got a circle, has a radius of 7. The length of arc AB is equal to 18 units, and again the radius is equal to 7. Find the length of chord AB. Now we're going to do this again with right triangle trigonometry. You could eventually maybe you could do law of cosine to do this end of this problem a little bit quicker. But whether you do law of cosine or whether you do your right triangle trigonometry like I will be doing for this video, because this is for my geometry class and we didn't cover law of cosine, you got to do the same thing in the first step. We got to take some information out of this triangle and get some more information about the triangle, because just knowing that these two sides are equal to 7, because they're both radiuses, is not enough information to find anything else about this triangle. So what information is given? How do we start this problem? Well, we pick the number that has a formula attached to it and let the formula tell us what to do. And that is arc length. We have an arc length of 18. Well, arc length, this is going to be a pretty lengthy problem, by the way. Arc length is equal to, let's see, arc length, length around a circle. Okay, so we've got to be starting with something about circumference of a circle, which is 2 pi r. It's diameter times pi as well, but we're going to focus on the radius. And arc length is just a percentage of the circle that I'm concerned with or I'm using. So that means that I'm going to find the entire circumference of the circle and then multiply by what part of the circle are we using. Well, that in the formula is theta. Again, I can't help but use these Greek symbols like my other math books do, over 3 60. I really need to be using, you know, I could be saying, I guess in my geometry terms, the measure of arc AB. And the measure of that arc is going to be the same as the measure of our central angle. That's where theta could be in its place. Well, arc length, the actual arc length between A and B, the length of that blue line, is equal to 18. And that is equal to, let's see what we got going on here. We're not, you know, we're looking for the measure of arc AB, which is going to be the same as the measure of our central angle. So that is going to stay there. But we do have 2 equals 2 times pi, which, well, let's just keep pi in there for a while, times r, the radius. Okay, r, yeah, we were told the radius was equal to 7, times the measure of arc AB, or I could say angle AOB or theta. I'm probably going to stick theta back in there, it's easier to write, over 360. Well, 2 times 7 is 14, so we have 18 is equal to 14 pi over, I'm going to go ahead and pull this 360 out, times the measure of arc AB. Go ahead and leave that in there. Now, I'm looking for the measure of arc AB, the number of degrees. Okay, well, I'm going to get to a point where I'm going to need some decimals here. 2 pi, or 2 times 7, 14 pi, I'm looking at my notes and thinking at the same time. 14 pi divided by 360 is equal to 0.122. So you have 18 equals 0.122 times the measure of arc AB. Divide both sides by 0.122, and the measure of arc AB is equal to 147.5 degrees. And how do I know it's degrees? Because I've got a degree measure in here of 360 degrees. I guess I put a little degree mark on there. Okay, now that means that, again, the measure of this arc in degrees is equal to 147.5 degrees. That also means the measure of my central angle is 147.5 degrees. Okay, what the heck were we trying to find in the first place? Chord AB. Now, if you've studied law of cosine, you've got 2 sides of a non-right triangle and an included side. So you could work through law of cosine and actually find the answer a little bit quicker than I'm going to do. But again, this video is, well, I mean, for you as well, but, you know, obviously for my students that I currently teach. And again, we didn't do law of cosine. We just stuck with the right triangle trigonometry. So I'm going to do that. So we're going to take this off. And we're going to, again, talk about right triangle trigonometry. We're going to drop an altitude down through this isosceles triangle. That altitude is going to become a perpendicular bisector to the chord, or the base of our isosceles triangle. See how this is tying together? That's what I kind of like doing right triangle trigonometry more in geometry. I keep getting to bring up these old concepts that I've covered in class and keep these ideas fresh in my students' mind. So I'm going to pull this right triangle out of here. Oh, and that is not only a perpendicular bisector again to the base, but a bisector of the vertex. So we're going to have, let's take this triangle out. And I'm going to go ahead and rotate it as well. So we have, we got A, B, O, and let's put a C here. So this is going to be the right angle where point C is. I'm taking this and rotating it that way, so this point is getting rotated up, and there is O. We have B over here. The hypotenuse of this right triangle that I'm creating, or between O and B, is equal to 7. And between O and B, C-O-B, C-O-B. Maybe a little bit more confusing actually trying to rotate this a little bit, but between COB, that's half of the vertex angle of our isosceles triangle, or half of the central angle. So 147.5, 147.5 divided by 2 is equal to 73.8 degrees. Okay, and we were initially looking for the arc, the distance between B and A. So what we're going to do is find the distance between B and C, that distance right there that has been rotated out, and double it for the entire chord when we're done. So we have 73.8 degrees, half of that central angle. We want to find the length of BC, which is the opposite side to this angle in our right triangle, and we want the opposite side, and we have the hypotenuse, and just for good measure, this is the adjacent over here again, even though I'm not going to find it. Angle, opposite, hypotenuse. I want the opposite. I have the hypotenuse again. That I guess was not really on purpose, but we're going to use the sine function again, sine of an angle is equal to opposite, which let's just call it BC, I guess. Why not? That is what we're finding. Over the length of the hypotenuse, which is equal to 7. We're going to undo this division of 7 by multiplying both sides by 7. That means that BC, if you were in a straight algebra class, you might be thinking this is B times C, but in geometry that's the length of a segment. 7 times the sine of 73.8 is 6.72. And again, remembering we are finding just the distance between B and C, not the entire chord. This is perpendicular, this is bisecting the chord again, so the length of AB, or chord AB, is going to be equal to 2 times 6.7. Can you get? I'm getting excited because I'm almost done, and you get to go do your homework here in a second. 2 times 6.72 is equal to 13.4 units long. And that is the end of my example. Hopefully this helped you understand this concept, and now it's time for you. Go do your homework.